This video covers sections 4.1, 4.2, and 4.3. And we just finished in chapter 3 talking about linear equations in two variables. When we talk about that, we're talking about things like y equals 1/2 x plus 3. Or we're also talking about things like we see here in the first equation of the first example, 7x plus 3y equals 13. What both of those equations have in common is they both have an x and a y. And we learned that when we graph equations like that, we get a line. Like this first one is going to have a y-intercept at 3, and then a slope of 1 over 2. So we rise 1, run 2, and we get a line kind of like this. And each solution to one of these linear equations is a point on the line. So the first question we want to ask is, when we're talking about systems of linear equations, and when we're talking about a system of linear equations, we're not talking about one equation, but two equations combined together. And we want to know if an ordered pair, say -2, 9, is a solution to the system of equations. If it is, it has to be a solution to both equations. So the first thing we're going to do is we're going to check in 7x plus 3y equals 13. So we're going to plug in, for the x, we're going to plug in -2, because remember, in ordered pair, x comes first and then y. And then we have plus 3 times y, but y is 9. And that should be equal to 13. 7 times -2 is -14. And 3 times 9 is 27. -14 plus 27 is in fact 13. 13 does equal 13. So -2, 9 is a solution to the first equation. Let's now check the second equation. We have x minus y equals -11. So I have -2 minus 9 equals -11. So really it's a -2 plus a -9, which is -11. -11 equals -11. It checks out, so yes, -2, 9 is a solution. Let me say it one more time. Because -2, 9 is a solution to both equations in the system, it is a solution to the system. Now, in general, when we have a linear equation, like that first example I gave you, its graph is a line. How many solutions does that line have, or how many solutions does that equation have? Remember, in general, any point on the line is a solution. How many points are on that line is another way of asking the question. And we should remember from last chapter that there are an infinite number of points on the line, or also an infinite number of solutions. Which brings us to the idea of a linear system, because now we're not just talking about one line with an infinite number of solutions. We're now talking about one line and a second line, so two lines. And really there's three different cases that can happen. There's three cases or situations. The first case is that we have two different lines. First line, say, is in red, and then let's say the second line is in blue here. Well, in this case, the red line has an infinite number of solutions, the blue line has an infinite number of solutions, but there's only one place where both lines have the same solution, and that is right here in the middle where they intersect. So in this situation where they intersect, there is one, we'll say, unique solution. That's one case. Case 2. Again, we have two lines. We have a red line. We have a blue line. These two lines are not intersecting. They are parallel lines. We have parallel lines. We have no solution. Because are there any points that are common on those two lines? In other words, will they ever intersect? And visually, of course, we can see that the answer is no. Parallel lines never intersect, which means there's no common solution between the two lines. There's a third case. This is our last one. And again, we have two lines. We have a red line. And then we have a blue line, which happens to be the same exact line. And in this case, when we have both lines are the same line, we have, how many places do those lines intersect? Hopefully you're thinking an infinite number of times. And in this case, there are, I'm going to write it up here, there are infinitely many solutions. Infinitely many solutions. So just to review, we can have one unique solution, we can have no solution with parallel lines, or if both lines are the same line, there's infinitely many solutions. We got some definitions down here. The first definition is what an inconsistent solution is. Or an inconsistent system. If a system has no solution, it is called inconsistent. Systems with no solution are inconsistent. If a solution has a system, it is called consistent. Okay, if a system has one unique solution, it is called independent. The two lines are independent of each other. If a system has infinitely many solutions, the one line depends on the other, and we call the system dependent. So we have consistent and inconsistent, and dependent and independent. So the only one of these three cases that's inconsistent is the second one. This one right here is inconsistent. The other ones are consistent. And then situation 3 is dependent. So let's look at an example. This first section, we are just going to solve systems graphically. In other words, we're going to visually graph both lines and see if there's one solution, no solution, or infinitely many solutions. So this goes back to being able to graph like we learned last chapter. We have two lines here, and because it's a system, and so we want to graph both lines. We want to graph both lines on the same graph. And to do that, we need to have it in a form that is easier to graph. So if I have x plus 2y equals 6, it would be nice if this was in slope-intercept form. So I know that I can make this 2y equals negative x plus 6. Change sides, change signs. So I'm going to move that x to the other side. And then after that, I'm going to divide everything by 2. Of course, we can think of this as like a 1 in front of the x. And so this equation becomes y, because the 2's cancel, becomes y equals negative 1/2 x. 6 over 2 is 3. That's the first line. It's the same as that one. We just wrote it in a different format. And so this one we know has a y-intercept at 3, so I can put a point there at 0, 3, and then it has a slope of -1 over 2. And remember, when it's negative, instead of rising, we drop, so we go down 1 to the right 2. And if I go ahead and graph that, you just draw a straight line through those points. When we do that, it looks something like that. Okay, now we can also do the same thing with the second equation. The second equation was 3x minus y equals 4. Again, move that x term over to the other side. It's a positive 3x, so when I move it over, it's going to be a negative 3x. 4 is positive. And we almost have in sloped-intercept form, except that there's this negative in front of the y. And so that negative is kind of like there's a -1. So one way of changing this is just to divide everything by -1. Just like in the first equation, we divided everything by 2. So we divide by -1. When I do that, -1 cancels on the left side, and we get just y. -3 divided by -1 is positive 3x. And 4 divided by -1 is -4. So this one has a y-intercept at -4 and a slope of 3. So we can think of this as 3 over 1. So we're going to rise 3 and run 1. Of course, from there, if you rise 3 and run 1 again, you get to that point on the first line that they have in common. So we can see here that those two lines will intersect right here. That's the point 2, 2. And that's our answer. In this case, our solution to the system is the point 2, 2. It's the one point where both lines have the same solution. Now, we know graphing can be a little bit tedious. So there's got to be some other ways to solve these systems, and that's what the next two sections are about. Section 4.2 is one way. It's called the substitution method. And then section 4.3 is a second method called the addition or elimination method. So let's take a look at section 4.2. And the name of this method, the substitution method, has everything to do with how we're going to try to solve this system. We're basically going to substitute one equation into the other. And so if I look at my first example and I want to solve by using the substitution method, you'll notice that the second equation, y is isolated, which is going to make substitution pretty easy because we already have what y is equal to. And so what we can do is I can take what y is equal to 2x plus 2, and I can substitute it in for y in the first equation. I can substitute (2x plus 2) for y in the first equation. And so if I take the first equation, it's 5x minus 4y equals -2. And so far in this class, we pretty much only substituted values in. But remember that when we substitute, you're always going to want to put those values that we substitute, or in this case, an equation or an expression, we're going to put that in parentheses when we substitute. So this is going to be -4 times y, but we're going to put in parentheses there. What are we putting in place of y? We're putting 2x plus 2. and then it still has equals -2. That's the right side of the equation. So again, all I did was I took that 2x plus 2 and I plugged it in for y in the first equation. So now we can go ahead and solve, because notice now we just have x, so we should be able to figure out what x is. What are we going to do here to simplify? We're going to distribute. Now remember, we don't just distribute 4, we distribute -4. So it's -4 times 2x is -8x. And then -4 times 2 is -8. That equals -2. Combining like terms, 5x minus 8x is -3x. Minus 8 equals -2. Want to change sides, change signs, move this -8 to the other side, it becomes a +8. And that'll give us -3x equals 6. Divide by -3. 6 divided by -3 is -2. Now one of the things you're going to want to be very careful of when you are working these problems is signs. You got to have your signs right. Everything will be thrown off if you don't have the right signs. And you want to get full credit for the problem, so make sure you're careful with your signs. Now remember, a solution, our answer, should be in a point. It should be an ordered pair. It should have an x and a y. We only found the x. Now we have to find the y, and this is where we substitute again. And you can substitute back into either equation. We can take this, and we can substitute into either equation. And I usually like to pick the one that's going to be easiest, and because y is already isolated in the second equation, I'm going to substitute into the second equation. So when I go ahead and plug into the second equation, I'm going to have y equals 2 times x, but x is -2. Remember, we're using this equation right here. Plus 2. This is -4 plus 2. -4 plus 2 is -2. So I get y equals -2. So my answer is -2, -2. And we have it. We found our answer. Now there's a second example here where we're going to need to do a little bit more work, because the first example we already had y isolated. Y was by itself. But you'll notice in the second example we have two equations, but neither one of them have solved for one of the equations, or for one of the variables. So if I look at these, which equation is going to be easiest to solve for a variable? And it doesn't always have to be y that we solve for. It can be x that it's solved for as well. So for example, if I took the second equation, 3x minus 2y equals 5, and I solve for, say, x, that would be 3x, move the 2y to the other side, it becomes a +2y plus 5. You don't have to write this in your notes, but I want you to think about this. Then we divide by 3. We got x equals 2/3 y plus 5/3. And then we would have to substitute this into the other equation. Do you see the problem with this? Is that we have fractions, and nobody likes to work with fractions. And the reason why we got fractions is because we had this 3 that was in front of the x. So that's always going to be an issue if you have a coefficient in front, or a number in front of the variable that you're trying to solve for. Notice in these two equations, every single variable has a coefficient or a number in front of it, except for the x in the first equation. So what I'm going to do is take that first equation, and I'm going to solve for x, because that's going to give me the cleanest substitution. And that's going to give me x equals, move that -4y to the other side, it becomes a +4y minus 5. And then I'm going to substitute. Then I'm going to take what x is equal to. It's equal to 4y minus 5, and I'm going to plug it in for x in the second equation. Remember, when we plug in, we use parentheses, so this is going to be 3 times x. Here's our parentheses, but x is 4y minus 5, and then we have minus 2y equals 5. Go ahead and distribute. 3 times 4y is 12y. 3 times negative 5 is negative 15. We have minus 2y equals 5. We keep going, combine like terms. We have 12y and negative 2y. When I combine those, I get 10y minus 15 equals 5. Move the negative 15 to the other side, it becomes a positive 15. And when I add that, I get 10y is equal to 5 plus 15, which is 20. Divide by 10, we get y equals 2. Now remember, that's just the y value. We need an x and a y. So now we can take that and substitute back into either equation. I'm going to go ahead and pick the first equation that we already manipulated, because then we know that x is equal to 4 times y, but y is 2 minus 5. 4 times 2 is 8. 8 minus 5 is 3. So x equals 3, and our answer is 3, 2. This is how we solve a system of equations using the substitution method. Okay, so this brings us to section 4.3, which is the third and final method for solving systems of linear equations. And this is called the addition method or the elimination method. And we're going to take advantage of doing exactly what the name says, just like the last method was called substitution. So we substituted. Here we're going to add. It's the addition method. We're going to add two equations together, and when you do that, you add up the left side, which in this case we would add a and c and get a plus c, and we'd add the right side and we get b plus d. And we want to do this though in a strategic way, which we'll talk about in just a second. I want to also review that there are three different things we can get when we solve a system. We first of all can get one solution, we can get no solution, or we can get an infinite number of solutions. And we're going to look at some examples in this section where we have each of those three cases. So let's first look at this example here, and let's talk about what happens when we add these two equations together. So I'm going to add the left side first, and notice that these equations are lined up. So the x's are lined up, the y's and the numbers. So if I add the x's, 3x plus 5x is 8x, and negative 2y plus 2y, well, look, those have the same numbers but the opposite sign. So what's going to happen with those? Those are going to cancel, so there's no more y's. And then the other side, negative 18 plus 2 is negative 16. Now this is really nice because now I can divide both sides by 8, and I got x really quickly. I got x was equal to negative 2. And of course we know that when we solve a system, it's more than just x. We need a y too, so we need to figure out what y is. But we know how to do that because of the substitution from the last method. But what happened at the beginning of this problem, where the y's canceled, that is the idea of the addition method. Or remember, it's called the elimination method. And I like elimination as a name too because the y's were eliminated. And why were they eliminated? They were eliminated because we had a positive 2y and a negative 2y, which are opposites, so they cancel. So if I look at the next example, notice that what we have is, again, two equations. X's are lined up, the y's are lined up, and the numbers are lined up. But do we have the same thing that we had in the last one where we had the same numbers but different signs. We have 3 and 10. Those aren't the same. And we have essentially a 1 here, a -1 and a -5. Those aren't the same. So we're going to need to do a little bit of work here. And we want to do the least amount of work. So if I look at the x's, the smallest number that 3 and 10 can go into would be 30. So I would have to multiply the top equation by, say, 10 and the bottom equation by a number as well, like -3, and then I'd get a +30 and a -30. I know I said that kind of fast, but we'd like to stay away from having to multiply both equations by something. Sometimes that'll be necessary, but not always. Now if I look at the next ones, remember that this is like a 1 in front of the y. There's a 1 and a 5. Well, both of those numbers go into 5. So if I multiply the top equation by, say, -5, and multiply it by -5, then the top equation, well, 3 times -5 is -15x. -1 times -5 is plus 5y. And 7 times -5, that's equal to -35. Let's not touch the second equation, so we'll just rewrite it. That's 10x minus 5y equals 25. Now notice when I did this, I didn't just multiply by 5, because if I multiplied by 5, I would have got a -5y. And then if I had negative and negative, those won't cancel. I needed to multiply by negative because a -5 times a -1 gave us a positive. Now these two terms are opposite signs. They cancel. This gives me -5x for the x's, and -35 plus 25 is -10. Now I can divide by -5, and I get x equals 2. Now, I'm not done yet because I do still need to solve for y. And so if I take the first equation, the 3x minus y equals 7, and I plug that 2 in for x, I get 3 times 2 minus y equals 7. 3 times 2 is 6. 6 minus y equals 7. Move that 6 to the other side, it becomes -6. I get -y equals 7 minus 6, which is 1. And I can divide by -1, which gives me y equals -1. So my answer is 2, -1. Let's take a look at another one. In this next one, I can't multiply 2 or 3 by anything to get the other number, and I can't multiply 2 or 5 by anything here. So this is one of those situations where I'm going to have to multiply both equations by constants to get one of the variables to eliminate. Notice in our first equation, we eliminated y's. In our second equation, we also eliminated y's. Let's try in this one to eliminate the x's, because it doesn't have to be just y's that are eliminated. So if I was trying to eliminate the x's, notice that both 3 and 2 go into what number? They both go into 6. And remember, I can't just have +6. I need one to be a +6 and one to be a -6. So let's multiply the first one by, say, -2. And then let's multiply the second equation by +3. When I do that, the first equation becomes 3 times -2 is -6x. 2y times -2 is -4y. And that's equal to 3 times -2, which is -6. And then on the bottom we have 2x times 3 is 6x. See, now we have those opposite signs, -6x and +6x. 5y times 3 is plus 15y. And 3 times 13 is 39. Now our x's are going to eliminate just like we wanted. Negative 4y plus 15y is 11y. And negative 6 plus 39 is 33. We divide by 11. And we get y is equal to 3. Of course, remember we have to find x as well. We can plug that 3 back into either equation. If I take the top equation, 3x plus 2y equals 3, and I plug in 3, I get 3x plus 2 times 3 equals 3. This is 3x plus 6 equals 3. Move that to the other side, it becomes a negative 6. So I get 3x equals negative 3. Divide by 3. I get x equals negative 1. So my answer is negative 1, 3. Take a look here at a few more examples. The next example, notice I have, again, if I add right away, nothing's going to eliminate. If I wanted to eliminate the x's, what would I need to have in front of this x? I would need to have a 3. So let's go ahead and take that whole equation and multiply it by 3. If I do that, I get 3x minus 9y equals 6. From the bottom equation, now we don't need to touch that. I get negative 3x plus 9y equals 6. Sorry, it doesn't equal 6, it equals what? Equals 2. We're not touching that one. And then I add, and look what happens. The x's cancel, the y's cancel, so I have 0 on the left side, and the right side equals 8. Is 0 equal to 8? No. So this is one of those special cases. It's not we get one unique solution. When you have a statement like this that's false, it's a false statement, that means that this is no solution. So those two lines were parallel lines. We have one more example here. Again, if I add right away, nothing is going to happen with these two equations. There's going to be nothing eliminated. But if I wanted to eliminate, say, the x's again, I would need to multiply the top equation by what? By negative 2, because that'll make it negative 10x, which is the opposite of positive 10x. So if I multiply the top equation by negative 2, I get negative 10x plus 2y equals negative 2. Bottom equation we don't need to change, just stays 10x minus 2y equals 2. And you may be starting to notice that something strange is going to happen again here, because the x's cancel, the y's cancel, and the numbers cancel, and I get 0 equals 0, which is not false like the last one. This is true. It's always true. 0 is always equal to 0. So this is not the special case of no solution. This is the special case of infinitely many solutions. Now going back through and naming these by our definitions we covered earlier in the video, this would be considered a dependent system. It has infinitely many solutions. This solution, this example here had no solution, so we called that inconsistent. In all of the other examples, this would be a consistent solution, or a consistent system. It does have a solution. And that does it with this video. Thanks. We'll see you in class.